G'day. To cover the chemistry content in this course, we will take you through some basics to let you know what to expect in the weeks to come. Our stories usually have a historic element to them, giving you the background to how we arrived at the medicines we are highlighting. In many cases, a molecular evolution has taken place to address problems with potency, selectivity, and safety before we arrive at useful medicines. As well as showing you these progressions through time, we will make comparisons between molecules to understand their biological actions. Or we will show you how they bind to their protein targets, such as enzymes or receptors. Throughout each case, chemical structures will be explored. So we need to gently introduce you to some organic chemistry. Let's start with what we are likely to encounter in the weeks ahead. We'll show you flat, two-dimensional chemical structures, like the one shown here. But what is it that we are actually looking at? Let's break this task into smaller pieces. First of all, we have letters, which represent atoms, such as N for nitrogen, S for sulfur, and O for oxygen. For carbon atoms, we can either indicate these by a letter, or they are placed at the intersection of two or more lines. As well as this, there are numbers, such as 3, where 3 indicates 3 hydrogen atoms. In general, we don't put all the hydrogen atoms on the structure, but we assume they are there. The lines are bonds between atoms, and in some cases we have 2 lines, and they can arrange into variously sized rings. At first glance, this may be daunting, but we'll take you through this slowly. Let's start with the chemical elements. Drugs comprise a limited number of chemical elements, as they are primarily organic in nature, meaning they usually contain carbon atoms. The common elements we see are listed in the word CHOMPs. Although we won't specifically encounter phosphorus in these chemistry modules, phosphorus is, however, vital as it's part of the backbone of our DNA. Other elements we will encounter include the halogens, such as bromine, chlorine, and fluorine. We can imagine this system to being like an alphabet. With letters, we can use these to form words, with associated grammar and spelling rules. And the same goes for molecules. We can't just throw together any old atoms. There are chemistry rules to follow. The words in this sense are molecules. So let's make some chemical structures. We'll start with butane, the gas that's often used to run our barbecues. The molecular formula tells me there are 4 carbons and 10 hydrogens. The structure can be written out as a chain of carbon atoms with their associated hydrogens. Having the hydrogen atoms and labelling the carbons can clutter things. So we can also represent butane using a simpler structure, just a set of 3 lines. The last molecule here is ethanol, and this comprises 2 carbon atoms and an oxygen atom. The oxygen makes a single bond both to a carbon atom and to a hydrogen. And all up, ethanol has 2 carbons, an oxygen, and the molecular formula tells us that it has 6 hydrogen atoms overall. Chemical bonds represent electrons shared between atoms that strongly tie them together. For this course, we will limit the discussion to that of single bonds, double bonds, as well as aromatic bonds. A good example of a molecule comprising single bonds is ethylene glycol, a substance often used as antifreeze in cars. Here we have 2 carbon atoms, each of which is attached to an oxygen atom via a single bond. And the single bonds are simply shown as a single line. Our second molecule is propene and is also known as propylene. It is used in the manufacture of plastics, such as polypropylene. The 2 carbon atoms on the right-hand side share a double bond, and to represent this we see two parallel lines. The next type of bond we will discuss is an aromatic bond. Shown here is benzene. We see a ring structure with 3 double bonds and 3 single bonds. We could, of course, draw this by moving the bonds around the ring. In reality, the bonds in the ring are shared, and we can represent an aromatic ring with a dotted line or even a circle. And what we didn't show you was that benzene also has 6 hydrogen atoms, 1 attached to each carbon. Other rings are also shown here, many of which we will encounter in this course. So far, we've drawn our molecules in 2 dimensions. What we need to do now is consider their 3-dimensional shapes. Considering our gas butane, each of the carbon atoms in butane makes 4 bonds. These are oriented in a tetrahedral manner, and this movie shows us a 3D depiction of butane as we rotate it around, where we can see that each carbon atom is attached to 4 other atoms. The number of bonds an atom makes dictates the shape of that molecule. But on top of this, we also have to consider flexibility. Using these tetrahedral linkages, we can also construct rings. On the left, we have piperidine, a 6-membered ring with 5 carbons and a nitrogen atom. The molecule adopts a shape that is dictated by the characteristics of each atom. Benzene, on the other hand, is very flat, and we can see this having rotated the structure by 90 degrees. Nicotine combines 2 types of ring structures, and we can now introduce the concept that most molecules can adopt different shapes. In other words, they are flexible. The bond we've highlighted here allows the rotation of one ring relative to the other. In this movie, we can see that nicotine can assume different shapes as the rings move relative to each other. However, not all of these shapes are favoured, as molecules need to obey certain energy rules. As atoms tend to avoid bumping into each other, this will favour certain orientations of the rings. This is one of those favoured orientations. Most drugs will interact with specific proteins in order to exert their biological activity. To keep this brief, we will only discuss 3 types of interactions that take place between drugs and their protein targets. Salt bridges occur between 2 charged groups, and a good example is the interaction between negatively charged carboxylic acids and positively charged amino groups. These bonds, which are electrostatic in nature, are usually strong and contribute to a drug's potency. Next up, we have hydrogen bonds, which mostly occur between groups with nitrogen and oxygen atoms and their associated hydrogen atoms. These too are electrostatic in nature, but don't involve the full charges we see in salt bridges. As such, they are less strong than a salt bridge. Importantly, hydrogen bonds are used by drug designers to provide specificity for the different protein targets. And finally, there are hydrophobic interactions. Hydrophobic groups are those which a chemist might describe as being greasy. These interactions occur between hydrophobic parts of the molecule and hydrophobic sections of the protein. In this case, these groups are able to interact together and avoid water. While these interactions in isolation are weak, indicated by the wavy lines, they play a significant role in drug protein binding, particularly when there is a good fit between the shape of the drug and the shape of the binding site. So, let's recap what we've covered in this chemistry introduction. We've talked about the usual chemical elements that we see in drugs and shown you some simple chemical structures. This meant we had to talk about the bonds between atoms and how we draw molecules. On top of this, all drugs have important functional groups which are important for binding to proteins and for their solubility. We also had to consider the shape of molecules and their flexibility. Finally, we touched on three important interactions that occur between drugs and their protein binding sites.